Behold Metal G, the cosmic behemoth that could put our sun to shame. Imagine swapping our modest star for this fiery giant. Its blazing glory would stretch all the way to Jupiter's orbit, leaving us mere mortals in awe of its sheer size. But don't get too comfortable with this stellar spectacle, because Metal G is a ticking time bomb, ready to explode in a cosmic showstopper. But wait, there's more. Scientists have been peeling back the layers of this celestial enigma, Betelgeuse, and what they found has left them scratching their heads in wonder. Its erratic dimming antics are throwing a cosmic curveball, defying the neat explanations we thought we had for stars' behavior. And that's not all. Picture this star's surface pulsating like a galactic heartbeat, challenging everything we thought we knew about how stars work. But here's where it gets really juicy. Betelgeuse isn't just shedding material like your average red supergiant. Oh no, it's putting on a fireworks display with its dust and gas nebula, flinging stellar stuff into the cosmos like it's going out of style. And if that's not enough, brace yourself for the magnetic madness happening on its surface. Who knew stars could have such a magnetic personality? So, as we continue to unravel the mysteries of Betelgeuse, one thing's for sure: the universe is full of surprises, and Metal G is leading the cosmic charge with its jaw-dropping antics. These discoveries have prompted scientists to reconsider Betelgeuse's ultimate destiny. While a supernova explosion is expected, the exact timing and type of explosion remain hotly debated. Some speculate that Betelgeuse's peculiarities may be influenced by external factors, such as nearby celestial bodies. One possible explanation for Betelgeuse's sporadic dimming and mass loss is the gravitational influence of neighboring celestial bodies, which could deform its outer layers. As a result, Betelgeuse serves as a lighthouse for rethinking ideas about stellar evolution. Beyond being a celestial spectacle, Betelgeuse's imminent supernova presents an extraordinary opportunity to study the demise of a massive star in unprecedented detail. The energy emitted by such an event could provide invaluable insights into Betelgeuse's supernova could stimulate nearby molecular clouds to produce new stars through triggered star formation, shedding light on the stellar lifespan and enriching the interstellar medium with heavier elements crucial for planetary and life formation. While the potential impact of Betelgeuse's supernova on Earth's ecosystem is speculative, the event holds significant implications for the fields of astronomy and astrophysics. Thanks to the James Webb Telescope, which has revealed previously unknown complexities in Betelgeuse's behavior, scientists have gained unprecedented insights into the dynamics of this enigmatic star. Better predictions of when Betelgeuse would go supernova have been made possible by the more exact observations of its size and temperature provided by the telescope. Models attempting to forecast the lifespan of large stars heavily rely on these measurements. But that's not all Betelgeuse has to reveal. Beneath its throbbing surface lies even more mysteries waiting to be unveiled. Recent observations by the James Webb Telescope have shed light on Betelgeuse's mysterious character, ushering in a new era of cosmic exploration, where every discovery raises more questions than answers. Among the giants of the universe, Betelgeuse stands out as an unmatched observational target. Situated about 642 light-years from Earth, this star, marking the shoulder of Orion, is clearly visible even without telescopes, appearing as a bright reddish star. However, Betelgeuse's pulsating nature, not easily discernible to the human eye, complicates matters for astronomers. Its irregular pulsations, causing substantial variations in brightness over time, have long baffled researchers. Recent studies have revealed that Betelgeuse's size is dynamically unstable, with its diameter changing dramatically, casting doubt on the stability of red supergiants. Moreover, Betelgeuse's surface is adorned with enormous spots, much larger than those on the Sun, caused by regions of strong magnetic activity. These spots further complicate the star's pulsation pattern, attesting to the tumultuous processes within and surrounding Betelgeuse. Recent observations suggest a complex atmosphere surrounding the star, consisting of expelled gas and dust. The sky offers a glimpse into the deepest secrets of stellar evolution. Its throbbing red light provides a breathtaking panorama and a window into the turbulent life of a dying star. When stars like Betelgeuse explode into supernovae, they collapse under the force of gravity, forming either neutron stars or black holes, depending on their initial mass. The aftermath of such cosmic events fundamentally alters the space around them, contributing to the stellar birth and death cycle. Neutron stars and black holes, remnants of supernovae, exhibit extreme characteristics, influencing their surroundings profoundly. Supernova explosions enrich the cosmos with elements crucial for planetary formation and life. Regarding the possible consequences of Betelgeuse's supernova on Earth and our solar system, its distance of about 642 light-years acts as a buffer, greatly reducing direct effects. Nevertheless, the event will not go unnoticed, potentially impacting nocturnal animals' behavior and providing a spectacular light show visible even during the day. In summary, Betelgeuse's impending supernova offers an unprecedented opportunity for scientific study, providing insights into supernova mechanics, the formation of neutron stars or black holes, and the synthesis of heavy elements. While the event poses no direct threat to Earth, its repercussions will reverberate throughout the cosmos, shaping our understanding of stellar evolution and the universe's dynamics. Would provide a one-of-a-kind setting for astrophysical investigations. By studying these remnants, we may learn more about the stellar evolution of massive stars and the characteristics of these phenomena. If you thought Betelgeuse's pulsations were at the pinnacle of cosmic mystery, get ready to delve deeper into the heart of stellar life and death. Reads the Rehook. The tale of supernovae is waiting to be told, a story of immense creation and destruction. Are there any hidden meanings in these cosmic pyrotechnics? Shall we discover? The explosion of a star known as a supernova is one of the most powerful cosmic events that has ever occurred. Supernovae are important for cosmic evolution in many ways, including the distribution of life-sustaining elements and the influence on star formation. Two main types of supernovae have been identified, each with its own unique cosmic origin. Involve a binary star system, in which a white dwarf star absorbs matter from its companion. When this white dwarf reaches a critical mass, about 1.4 times the Sun's mass, it collapses catastrophically, and a thermonuclear explosion occurs. While this type does not greatly enrich the cosmos with heavy elements other than iron, it is a very useful tool for measuring cosmic distances, because its peak brightness is consistent. At the end of their stellar lifetimes, massive stars that are unable to maintain nuclear fusion in their cores collapse under their own gravity, releasing their outer layers in a massive explosion. This is a key process in the galactic synthesis and distribution of heavy elements, such as carbon, oxygen, silicon, and iron. Depending on the star's initial mass, the collapsing core may transform into a neutron star or a black hole. At this point, Type 2 supernovae are born. Supernova explosions are known to produce heavy elements like gold, uranium, and platinum through nucleosynthesis, a process that is less often talked about, but is essential for the chemical evolution of the universe because it seeds subsequent generations of stars and planets with the building blocks of life. Beyond the synthesis of elements, supernovae can compress interstellar gas and dust, a process called triggered star formation, which rejuvenates star-forming activity and guarantees that galaxies will continue to evolve and be dynamic. In addition, supernovae release vast quantities of energy into the interstellar medium, which heats it and enriches it with heavy elements. This enriched medium then serves as the substrate for the next generation of stars and planets. Supernovae play a crucial role in the cosmic matter cycle, contributing to an ecosystem where stellar deaths give rise to new astronomical objects. The study of supernovae also sheds light on the basic physics of extreme situations, such as how matter behaves under very high pressures and temperatures, how plasma shockwaves work, and what neutrinos, those elusive particles that are crucial to the core collapse mechanism, are like. Learning about supernovae and what they mean not only fulfills our natural curiosity in the cosmos, but also sheds light on the processes that have molded the cosmic environment, revealing where all the materials that comprise our planet and the hypothetical Mus-Phi are three of the most interesting and massive stars in our galaxy, and they each bring something special to the cosmic stage. Betelgeuse, with a size of about 1,000 times the Sun's radius, is a red supergiant of enormous scale. Its luminosity, which fluctuates a lot and puts it in the top 20 brightest stars in the sky, is subject to large variations due to its pulsating nature, which, in conjunction with stellar winds, gives the impression of a dying star. Antares, slightly smaller than Betelgeuse but no less impressive, has a reddish glow and variable brightness that rival, and at times surpass, Betelgeuse's, depending on their respective cycles of variability. Antares' substantial mass, about 12 to 17 times the Sun's, and its own significant mass loss, highlight the diverse outcomes of stellar evolution among red supergiants. They are not to be overshadowed. Let us enter the domain of conjecture and think about Mus-Phi, a hypothetical star that pushes the limits of size and brightness even farther. With a radius of 1,500 times the Sun's, Mus-Phi would block the light from Betelgeuse and Antares, shining brightly enough to be seen across the galaxy. With a mass of about 25 times the Sun's, Mus-Phi would represent the upper limit of mass and brightness, a red supergiant illuminating the dynamics and variability of these cosmic giants. Investigating the histories and traits of Betelgeuse, Antares, and the hypothetical Mus-Phi sheds light on the phenomenal variety and activity of stars in our cosmos. The disparities in magnitude, luminosity, and mass among these colossal objects in the sky serve to underscore the intricacies of stellar evolution, while simultaneously serving as a reminder of the dynamic, ever-evolving character of the universe. Thinking about what will happen to these stars makes us realize that every star's story is an individual journey, adding to the grand narrative of the universe, a narrative that persistently modifies our perception of the universe and our role in it. We have seen the diversity of the universe as we have journeyed from Antares to Mus-Phi, but the question remains, what fate awaits our giant? The answer might transform our view of the colossus amid stars, yet it is not alone in its cosmic dance. Stellar evolution is a complicated process that differs greatly with star mass. By comparing the projected fate of our Sun with Betelgeuse, a big star, we can see the different outcomes of stellar life cycles. Red supergiant Betelgeuse is nearing the end of its life cycle, which is characterized by a spectacular supernova explosion rather than a peaceful cessation of stellar activity. This catastrophic event happens when a star of this mass has used up all of its nuclear fuel and is no longer able to withstand the inward pull of gravity. In the case of Betelgeuse, whose initial mass was estimated to be 10 to 20 times that of the Sun, the core collapse is inevitable, and a supernova will ensue, leaving behind either a neutron star or a black hole. On the other hand, the medium-sized Sun will undergo a considerably less violent death. It is now in its main sequence phase, gradually fusing hydrogen into helium in its core, and this process will last for approximately another 5 billion years. After this phase, the Sun will expand into a red giant, consuming Mercury, Venus, and maybe Earth. After this phase, it will shed its outer layers, forming a planetary nebula. What's left is a white dwarf, a dense cooling remnant of the star it once was, and it will gradually fade away over trillions of years. The Sun's future is very different from Betelgeuse's because of their starting masses. Massive stars like Betelgeuse have short lives and short deaths, using up their nuclear fuel much more quickly than smaller stars like the Sun. Their spectacular deaths enrich the interstellar medium with heavy elements, which helps to create new stars and planets. On the other hand, the Sun's gradual transition to a white dwarf will have less immediate influence on the universe around it, but its eventual demise will have a profound effect on the solar system, especially the inner planets. A knowledge of the stellar evolution of stars like Betelgeuse provides insight into the ultimate destiny of our Sun and shows how the cosmos is structured as a matter and energy cycle. The cosmic ecosystem relies on the recycling of materials that come from star and planet deaths. whether by supernova explosions or the shedding of planetary nebulae. Looking at the evolution of these two very different stars highlights the variety of ways stars can evolve over their laws of physics, but have distinct consequences depending on the mass they started with. These stellar behemoths, red supergiants like Betelgeuse, are among the largest stars in the galaxy, frequently exceeding sizes of 1,000 times the Sun's radius, and they play an important role in several cosmic processes. They are important stages in the life cycles of massive stars and significantly contribute to the chemical enrichment of the universe. The chemical enrichment of the interstellar medium is greatly enhanced by red supergiants because in their cores, nuclear fusion produces elements heavier than hydrogen and helium all the way up to iron in the periodic table. When these stars explode in supernova events, they release these elements into space, where they contribute to the material that can be used to form new stars, planets, and even life. This process is fundamental for the evolution of the galaxy because it ensures that future star systems will have the ingredients needed for planets and possibly life. It is believed that the last stages of red supergiants' lives, particularly during supernova explosions, provide breeding grounds for the creation of even heavier elements through rapid neutron capture processes, adding to the cosmic chemical diversity. This is due to the fact that these stars' cores are so hot and pressurized that they are able to undergo advanced stages of fusion, which would not be possible in smaller stars like our Sun. Theories of stellar evolution, our understanding of the evolution of massive stars, from main sequence stars to red supergiants and finally to supernovae or directly to black holes, pose new challenges and refine existing theoretical models that must account for mass loss, changes in luminosity, and the complex interplay of nuclear processes that define these giants' lifetimes. Red supergiants are an important benchmark for stellar evolution theories because their properties and behaviors shed light on this entire process, controlling the creation of stars. Red supergiants are key players in the dynamic balance of stellar birth and death in the galaxy, and the supernovae that often mark their end of life have a significant impact on star formation in the galaxy. Shock waves from these explosions can compress nearby molecular clouds, triggering the collapse of these clouds and the birth of new stars. These shock waves can disperse material, inhibiting star formation in certain regions, aids in the advancement of knowledge. At last, red supergiants are scientific discovery machines. Research into them has pushed the boundaries of our knowledge of stellar atmospheres, wind phenomena, and the final stages of stellar evolution. While observations of these stars test our preconceived notions and inspire new tools and approaches in the field of astrophysics. Finally, red supergiants like Betelgeuse are more than just interesting objects to look at. They play an important role in the cosmic ballet of matter and energy, which impacts not only the chemical composition of the cosmos, but also the birth of new stars and planets. Astronomers are still guessing about what will happen to Betelgeuse in the long run, but one thing is certain. It will eventually turn into a supernova, a cosmic event that ends its life cycle as a red supergiant. With its present volatility and mass loss, Betelgeuse is on the edge of this dramatic transition. But when exactly it will happen is anyone's guess. Estimates for when its supernova will go off range from any moment now to thousands of years in the future. An unprecedented opportunity to study the mechanisms of supernova events up close will be presented by Betelgeuse's impending supernova explosion, which will have a profound impact on our understanding of the universe. Data from this explosion could either confirm or refute current models of stellar evolution. Observing a supernova from a star that has been studied in its pre-supernova state would be a first in modern astronomy, providing insights into the causes and sequence of events leading up to these explosions. Its supernova explosion will be so intense that it may be visible to the naked eye from anywhere on Earth, even during the day, providing an astronomical show not witnessed for centuries. For a while, it will rank among the brightest objects in the sky, giving rise to a new star that will be visible to the naked eye everywhere. From a scientific point of view, The supernova will provide an opportunity for astronomers to observe the nucleosynthesis process, which is critical for understanding the formation and distribution of the elements necessary for life, as it in the explosion synthesize elements heavier than iron. In addition, the interstellar medium will be affected by the supernova shock waves, which may cause new stars to be born in nearby molecular clouds. This triggered star formation process is important for controlling the rate of star birth and star death in galaxies. On a larger scale, the heavy element enrichment of the surrounding space by Betelgeuse's supernova will add to the cosmic cycle of matter, which is essential for the construction of subsequent stellar and planetary generations, including those that may hold life. Rehook, we are on the verge of a revelation that could shatter the foundations of astronomy as our research of Betelgeuse and its cosmic siblings draws to a close. From this tale of the giant, what can we draw, and how does it relate to what is ahead in our own cosmic neighborhood? The last leg of our adventure will lead us to the deepest. Secrets of the cosmos await as we continue our cosmic tour, entering the mysterious realm of Betelgeuse, a red supergiant star that has fascinated astronomers and the general public with its massive size and imminent supernova. Betelgeuse is a living example of the universe's dynamic and ever-changing character, as shown by its pulsating, breathing nature and its substantial contribution to the enrichment of heavy elements in the universe. Through comparison, we have seen how Betelgeuse compares to other cosmic giants like Antares and Musfie, highlighting the diversity and scale of stellar phenomena. We have also investigated the possible impacts of Betelgeuse's supernova, a cosmic event that is expected to illuminate our night sky with unprecedented brightness, providing a unique opportunity to study star life cycles and the formation of the universe's building blocks. Furthermore, we have discussed the larger cosmic implications of red supergiants, their crucial role in chemical enrichment, and their contribution to stellar evolution theories. What's more, we have been able to speculate on the timing and impact of Betelgeuse's supernova, thanks to its eventual fate, which promises to add a significant chapter to our galactic understanding. As we wrap up this cosmic tour, it's worth remembering how magnificent Betelgeuse is and how it fits into the vast far from over, and we can expect new questions and new insights into the mysteries of the cosmos to arise before its eventual supernova. If you've been captivated by the story of Betelgeuse and the boundless marvels of the cosmos, then you might want to consider subscribing for more content. Our cosmic adventure is far from over, and there are countless secrets just waiting to be revealed. Come along with us as we keep exploring space, looking for new insights, and deepening our knowledge of the cosmos. The next chapter will bring even more discoveries, and we can't wait to share them with you. To join us on another cosmic voyage, hit the like button, subscribe to our channel, and watch the video on your screen.